Hi. Beginning linear algebra students, section 2.1, homework number 20 had a really interesting definition of skew-symmetrical matrices. This is from the book Linear Algebra with Applications, and the website will be below the video. And I'm going to show a walkthrough of mathematical thinking in that I know I'm not going to be right the first time, but I'm going to learn from each time I make a mistake and see what I can do to correct it, which can be a really hard way of thinking about math. So many students think, I have to be right the first time, and you don't. So the definition was skew-symmetric means that if I take the negative of the matrix, it will equal the transpose. So, sorry, the bunny was cute. So I picked a matrix. I just did 3 by 3, and I usually try to get the numbers like between 0 and 9 in there somewhere and make a couple of them negative. So yeah, this is a general matrix. And it's not really random, but it's not skew symmetric. I'll show you. If I take the negative of this matrix and the transpose of this matrix, I'm not seeing a lot of similarities here. So obviously it's not skew symmetric, but I did notice that the diagonals are the same numbers, they're just opposite signs. I also noticed that the zeros in here didn't change signs. In fact, 0 is not a positive or a negative number. It is 0, and it is the dividing point between negative and positive, but it doesn't have signs. So what if I put zeros down my diagonals? So I have to change the matrix, call it Z. What happens then? So I look at the negative and the transpose, and I see that, oh yes, the zeros worked out for the diagonals, but I'm still kind of flopping around on above and below, left and right sides of this matrix. So what if I use the idea of symmetric and kind of put in points that are the same? So what if I put in 2 and 2? Or if maybe I need to make one negative and the other positive, I put in negative 11 and positive 11. And then I have a change of signs, but the numbers are different, with negative and 5 and positive 6. So negative, let's see what we've got. So it looks like we had positive to begin with, only positive, and we ended up with negatives and positives, but they're not in the same matrix. So these two aren't equal, although the numbers worked out really well. When I look at 5 and 6, yeah, the numbers are not a match, but looking at the plus 5, negative 5, and then they're both negative in the upper right corner, negative 5 and negative 6, says I need opposite signs and they need to be the same number. So did 11 work, or negative 11? Actually it did, because I have a positive 11 in the 8th entry and positive 11, and I also match up with my negative 11s. So I just need to make one of these 2's a negative and this 5 a 6. And that will give me a skew-symmetric matrix, which is pretty cool. You notice that the negative matrix and the transpose matrix are identical. Yay! Now, so that's what skew-symmetric is, and you can see a couple other examples. Zeros matching across the diagonal, but the signs change. So, I'm not going to worry about A. I kind of felt like I showed that. B, you can take any matrix and divide it into two matrices where one is symmetric and the other is skew-symmetric. Now, I thought this was an awesome definition. So, back to my rando um, da, 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 matrix. So I like the transpose. Oh, this is number A. Okay. So transpose and I subtract them. So 1 minus 1, 2 minus -4, 3 minus 5, and so on. And I end up with zeros down the diagonal and matching entries across the diagonal with changing signs. So yeah, that is skew symmetric. I just showed a random example. Now, if I really wanted to be official, I'd probably use things like A sub 1, 2, and A sub 2, 3. I kind of like this example. And I'll finish as fast as I can because part B is what I was really, really intrigued with. So, given your rando matrix, you should be able to divide it into something that's symmetric and skew-symmetric. So I know the skew-symmetric has zeros, so I decided I'm going to put all the diagonals into the symmetric one and zeros in for my skew-symmetric. So if I add these two together, I'll go back to the W. Now, I'm not there yet, so I'll try another idea that I came up with. I was actually looking at the 3 and the 5, and I realized that 5 is 4 plus 1, and 3 was 4 minus 1. So what if I put 4's in these upper and lower corners, and plus or minus 1 in my skew symmetric? So that means I've got to have positive 4's in the S matrix, and the T needs to have, I had to look at it for a bit. The positive one is in the lower left, and the negative one's on the lower right, even though the range itself was -1. So I thought, okay, let's see if it works for two other points. 2 and -4, average is -1. The range is 2 minus 2, or 4, -4 minus 2, which is -6, divided by 2 is -3. So I'll have to make that plus or minus when I put in here. So S becomes, we've got a -1 diagonal going here, or a matched pair, and in the skew matrix, I've got the 3, and one's plus and one's minus. And again, I had to figure out which one was plus and which one was minus. Okay, so the last one, the match, or the two entries were 9 and 0. So the average with that was 4.5. And surprise, when I'm looking at the range, it's also 4.5. So I'll put the positive 4.5 into S, and I decided the negative 4.5 needed to go above the 0. Because that way I'll, 4.5 minus 4.5 is 0. So I just divided it into a symmetric and skew-symmetric pair, which we might be doing in the future, so I thought it was worth pointing out. And so, thinking mathematically, I thought, all right, let me come up with some formulas. And it didn't look very pretty. Averages plus diagonals, ranges with zeros for diagonals, and then I have to throw in a plus or minus. This is... so I did kind of say, all right, I need a different method. So I went to the answer in the back of the book for part C and realized that here's the same thing for part B, A equals S plus W, and then we have two formulas for S and W. And two numbers or two mate, let's just call them two objects added together and divided by 2 gives you an average, and one, the matrix minus its transpose divided by 2 gives us the range idea. And they don't even have plus or minus. So I actually went through, um, oh, let me pause. Sorry, I'm not sure where that word came from. Okay, so matrix, transposed matrix, I add them together, I do get a matrix that's symmetric. And when I divide it by 2 or multiply by 1/2, my matrix I'm moving the screen just a bit, there we go, is the same as the one I calculated that took 5 slides to do. And if I look at the W, this is the one that's skew symmetric. So I have my matrix in its transpose, and I subtract. And yes, I do get zeros down the diagonal, and yes, this is a skew-symmetric function. Now what's cool is when I divide it by 1/2, I get the same numbers as what I just found before with t. So I think these formulas right here might be good ones to know. All right, let me move the screen one more time. Okay, skew-symmetric matrices. I want to take a note for them for, say, a test or a final. I don't know what your teacher might come up with. Thank you.